Welcome to a lesson with Dr. Powell. Let's take a look at finding maximum or minimum values of f, x, y is equal to 2xy when we're concentrating on staying on the following curve. X squared over 4 plus y squared is equal to 1. Now, following the idea from the previous video, what we have is we want to find out points x, y, where the gradient of f is going to be parallel to the gradient of some function g that this is the a level curve of. Well, if we just let g of xy be equal to x squared over 4 plus y squared, that works because this would just represent the values of x and y where the output of this function is 1, so you get a level curve there. So that's great. So then we're thinking of this curve as being a level curve of this function. So we're looking at where this is going to be parallel, so equal to a constant scalar multiple of the gradient of g. So we can calculate the gradient of f by just taking derivatives. We get so doing so, we end up getting 2y comma 2x, so the derivative with respect to x is just 2y, derivative with respect to y is just 2x, considering the others as constant. And then over here we get derivative with respect to x would be just x over 2 because it's 2x over 4, and then we have 2y. Okay, and then we need to find our, we can equate components, all right? So this lambda multiplies in, and then you can kind of equate the x components and the y components. So 2y is equal to lambda x over 2, and we also have 2x is equal to lambda 2y, just like that. Okay, and then looking at this, notice that x is already solved for, and maybe this is just algebra at this point. We have 2 equations and 3 unknowns, but we're going to be looking at different conditions and different cases and things, trying to narrow down what the possibilities are. There's various ways of doing this. Some ways are more advantageous than others that give us more ideas than we could otherwise have. But whatever we do, let's just remember that this is actually 3 equations, 2 unknowns, because we're actually on this ellipse. So we really have 3 equations. So just keep that in mind. And that'll help us narrow things down a little bit more. Okay, so why don't we begin by thinking of lambda as kind of extra here. And so it'd be nice, what if we just solve for, notice how lambda just appears as a constant here. Why don't we solve for lambda in each case? But if we do and we divide by something, just remember that that we're taking away the possibility that that thing that we divide by is 0. And so we got to check that case. In particular, if we divide, let's see here. So just keep that in mind. So if I divide by x over here, then I have to think, okay, x equals 0. I need to check that possibility. Check. Then I'm gonna get, so when I do that, I'm gonna end up getting 4y over x. So I divide by x over 2, so multiply both sides by 2 over x. I get this is equal to lambda. And if I solve for lambda over here, I could set that equal to that as well and get a nice equation just on that side. So if I do that, I'm getting x over y. But if I did that, I need to also put off the side that I need to check the case that y equals 0 because I divided by it. That's always important to kind of write that off the side. So we'll check those cases. So then, and just remember, we also have this equation we're working with. Okay, so then in that case, since y and x are not 0, we have this well defined. We could cross multiply both sides by xy, and we'll end up getting 4y squared is equal to x squared, which allows us to make a nice substitution up here in this equation for x squared being 4y squared. So we end up getting just y squared even after we cancel the 4's, plus y squared is equal to 1. So we get 2y squared is equal to 1, or y squared is equal to a half. So that means that we're getting y is equal to plus or minus square root of a half. So basically, if these things are not true, then we must have this. Okay, so we've kind of narrowed down some narrowed down some possibilities here. Okay, so we have this right here to look at. And since we're on an ellipse, that actually determines exactly what x is. I mean, we could take a look at that. So when y is plus or minus square root of a half, then y squared is just a half. So if we say 1 minus a half on that side, we'd end up just getting x squared over 4 is equal to a half even. If you plug that in for y, whether it be plus or minus, you'll end up getting this. So which would be 2. So it looks like x is going to be plus or minus the square root of 2. Okay, so actually so if y is plus or minus here, you also have these possibilities here. So it looks like there's like 4 points going on that we need to be aware of and be looking at to check. But also we have these. So let's look at this for a minute. What happens when x is 0 and y is 0? Well, let's just kind of look over here. When x is 0 and y is 0, well, when they're both 0, this equation is not satisfied, so we can't have that. Okay, so let's just check if 1 is 0. Okay, well, if one of them was 0, like this is 0, well, that actually forces in this equation y to be 0, so they both have to be 0. No, that doesn't work. So we're free from those. So really, the only possibilities we have left over are, let's write down these points as follows. We have, so x is plus square root of 2. Yeah, x is plus square root of 2. And well, actually just these 4 points, plus minus and plus minus. Either way, for this, so for y is, sorry, do that. That works. Okay. So that's for x and y. So we get 4 points on the ellipse. So in this particular case, this ellipse looks kind of like this, and we're looking at, yeah, kind of roughly 4 different points here on the ellipse. So these are potential. So what is this? This is when we're parallel, when it's momentarily parallel. But I mean, if it's parallel, like anything, it could go like that, and that wouldn't represent a maximum. It could just kind of go through that way. What we would like is if the for the level curve, I mean, I guess, yeah. So the level curve, we have to be a little bit careful here, I guess, if it's passing through. Yeah, like how is it tangent to the level curve? Is it tangent? Is it going to be a maximum? So we have to kind of think about that a little bit. So the way we kind of do that is we just simply plug in these 4 points into the function, and we kind of determine what the biggest one is. Okay, so in order to find the maximum, so if we plug these in, let's see, in this particular case, so we plug in that. Actually, it looks like x times y. That's just going to be, these are just reciprocals of each other, so they just cancel. So you end up getting plus or minus 1. So really, you end up getting plus or minus 2. I guess the points that would give you plus 2 for the output, that would be a probably local maximum, because we kind of have to have on this closed thing. We actually know that we actually achieve maximas or maximums because it's closed here, and we have a nice, and this function right here is continuous on this nice kind of enclosed set. There's no way that you could, since it's defined, it's going to have to come up but then continuously wrap back around. And so you end up getting maximums and minimums for sure. So based upon that idea, so such that local maxes and mins have to occur and it's reasonably smooth, then you know that these are actually local maxes and mins, especially if it's because they have to exist there. And so we're getting a +2 and a -2. So the maximum is +2 and the minimum is -2, and they occur at the corresponding points here. In fact, we could even check this. So for +2, that would be these 2 points right here. And so these two would be maximas of this function, restricted to here, and these two right here would be minimums. Okay, minimums on that function restricted to that ellipse. Thanks for watching.